All right, the function is defined like that from 0 to 3. The point 0, 1 lies on the graph of f. There's max at q. Sketch the graph of y equals f at x, labeling the points p and q. So this is with graphing calculator. So here's the things you want to include. The x-intercept, the maximum, and here's the point 0, 1. And you need to include the asymptote here. Okay, so now show that the derivative is that. So we're going to do the first times the derivative of the second plus the derivative of the first times the second, and we can pull out an e to the negative x, and on the inside is going to be a negative because of that. Negative 2x plus 1 plus 2. So e to the negative x, and then we're going to have a negative 2x and a negative 1 plus 2. So that's that. Find the exact coordinates of q. Okay. So we know it's going to be 0.5, 1.2, 1.306 approximately. So if we set our derivative equal to 0, e to the negative x never is 0. So when we do 1 minus 2x is 0, we get x is 1/2. And then if we sub that back in to the original function, which is going to be 2 times 1/2 plus 1 e to the negative 1/2, and that's going to be 2 e to the negative 1/2. So coordinates are 1/2, 2 e to the negative 1/2. Now C, the equation f at x equals k, where k is a real number, has two solutions. Write down the range of the values of k. All right, so if we have, so this is only good from 0 to 3, okay? So we're only from here to here, and it starts at 1, okay? So if we draw a line like this, where it intersects 1 again is the last time that it will have two solutions. So this is going from 1, y equals 1, up until that maximum point, okay? So 1.21, or our e to the, or whatever it was, 2e to the negative 1/2, okay? So, yeah. All right, so then D, given their second derivatives that show the curve only has one inflection point. Okay, so we know e to the negative x never equals 0. So negative 3 plus 2x will. So x is going to be 3 over 2. So that's the point of inflection. All right, 42. Consider the function that x can equal 1. Part of the graph of f is shown, vertical asymptotes, vertical and horizontal shown. Write down the equation of the vertical, well, that's at x equals 1. It's given that stuff. Write down the equation of the horizontal asymptote. Well, if we would expand out the x minus 1 squared on the bottom, we would have the same degree top and bottom, and we would see that y equals 2. And also, as x gets bigger from the positive, like x gets larger, goes to positive infinity, we see it's approaching 2. And as x gets smaller, x is approaching 2. So, yeah. C, show that the derivative, first derivative. All right, so we're going to have v on the bottom, v squared. And then we're going to start with v and times the derivative of u, which is 4x minus 13, and then minus 2x squared minus 13x plus 20 times the derivative of v, which is 2x minus 1. All right, so we have an x minus 1 in common. And then on the inside, we're going to have x minus 1 times 4x minus 13. And then minus 2, that 2. And then 2x squared minus 13x plus 20. And then that is all over x minus 1 to the 4th. And one of those will cancel. So when we would distribute this out, we're going to have 4x squared minus 13x minus 4x, so minus 17x plus 13. And then we're going to have minus 4x squared plus 26x minus 40. And then that's over the x minus 1 cubed. So then we will have that gone. And then negative 17x plus 26, that's the 9x. And 13 minus 40 is negative 27. So we've showed that. And the second derivative, okay, well, we're going to have the second derivative. We're going to have x minus 1 to the 6th, v squared, and then x minus 1 cubed times 9 minus 9x minus 27 times 3x minus 1 squared. So then we can pull out an x minus 1 squared. And then on the inside, we're going to have 9x minus 1. And then we're going to have minus 3 times 9x minus 27. And then x minus 1 to the 6th, which will cancel and be 4. So then if we distribute this, we're going to have 9x minus 9 minus 27x plus 81 over x minus 1 to the 4th. So that's going to be negative 18x plus 72 over x minus 1 to the 4th. So that is what we got, 72 minus 18x over x minus 1 to the 4th. Using the values of the first and second derivative, explain why the minimum must occur at x equals 3, and then the point of inflection. Okay, so first of all, if we set the first derivative to 0 and cross multiply, we just have 9x minus 27 is 0. So x is 3, and if we sub that into the second derivative, we're going to have negative 18 times 3 is negative 54 plus 72 over a positive number. So this is greater than 0, which means it's concave up, which means there's a minimum at x equals 3. Okay, and then there's a point of inflection. Write down the coordinates of this point. Okay, so that's when we set this equal to 0. And they tell us it's a point of inflection, so we don't need to worry about it. Like showing it's a point of inflection. So cross multiply by the denominator. And then we're going to have negative 72 over negative 18, which goes in 4 times. So at x equals 4, there's a point of inflection. And they want the coordinates, so we need f at 4. And the original function, is, here, I'm going to do it up here. F at 4 is 2 times 16 minus 13 times 4, 52 plus 20 over 3 squared, 9. So then that's 32, negative 20, so 0. So the point of inflection is at 4, 0. Okay, consider this function from negative 2 to 2. Graph is given. Let P and Q be the stationary points. Find the x coordinate of P and Q. So here's the graph, and I've already found the min and max. So we have P's x-coordinate is negative 1.15. Q is 1.15 positive. And if we want two solutions, we have anywhere. So there's two solutions. And then 2 is like here. Okay? And negative 2 is about like there, it looks like. I'm just looking at the calculator. So there are two solutions. If we go above that, it's only one solution. If we go below that, sorry, that's 3 solutions. And then here's 3 solutions. So the only times we have one solution is at y equals 1.15. And also here is going to be one solution. Y equals negative 1.15. Okay, so outside of that, like above those has one solution, and in between those has 3 solutions. All right, G's that. Okay, G prime. Lots of practice with derivatives. So 4 minus x squared on the bottom. No, sorry. I was looking at the wrong thing. Okay, so we have first times the derivative of the second times negative 2x, chain rule, plus the derivative of the first times the second. So we know what we're going towards. So we've already got this part, which is nice. And then this is going to be, negative 2x to the fourth over 4 minus x squared plus 3x squared natural log 4 minus x squared. Sketch the graph of G prime. Okay. So I'm sure you can do it with the graphing calculator. So I'm going to show you this way to do it with the graphing calculator. Get another function, and if you go into this little thing here, you can get this, and then you do dx with respect to x, and then you can put in your original function, which is x to the third times natural log 4 minus x squared. I'm sure this would never come up, but if it did. So that's the graph of the derivative of so the red is the derivative of the blue. So then if we want to write down all values of w for which the red line has 2 solutions. So here, that would have 2 solutions. And if we move, so from there we have 1, 2, 3, 4, always 4, and then 3, and then below that minimum we have 2 again. So we need whatever the maximum is. So if we find the maximum, it should be the same value, which ends up being 2.69. So at y equals 2.69, that's this line here. And then if we find the minimum, we get, it's 0, 0. So that's 0, 0. So anything y less than 0, because that will have 3 solutions. Anything less than that will have 2 solutions. All right, 44. The function's defined by that. More derivatives. Okay, so we have f prime. Start with x cubed and squared on the bottom. So so v times the derivative of u minus u times the derivative of v, and then that's going to be x squared minus 3x squared natural log x, x to the 6, we can factor out an x squared, 1 minus 3 natural log x over x 6, so that ends up being 4. Okay, so 1 minus 3 natural log x over x 4. Now, second derivative, x to the 8th, x to the 4, and then the derivative of that is negative 3 over x. The derivative of u is that. And then minus 4x cubed. So then we will have x cubed, so negative 3x cubed, minus 4x cubed, bracket 1 minus 3 natural log x over x to the 8th. And we can factor out an x cubed, and that's going to be negative 3 minus 4, and then over x to the 8th. So that will cancel, only 5 left. And then we have negative 3 minus 4, which is negative 7, and then plus 12 natural log x, and that's over x to the 5th. Okay, find the exact value of the x-coordinate of the max point and justify its max. Okay, so we'll set the first derivative equals 0, cross multiply by x to the 4th. So we're going to have 1 equals 3 natural log x. Divide by 3, write exponentially, e to the 1/3 is x. And then we need to substitute that into the second derivative. And that's going to be negative 7 plus 12 natural log e to the 1/3 over e to the 1/3 to the 5th. Okay, so this is going to be negative 7 plus 12 times the third, because natural log e goes away, so that's 4, and that's e to the 5/3. So this is a negative over a positive, so this is less than 0, which means it's concave down, so there's a maximum. Max at x equals e to the 1/3. So that's done. Solve the second derivative equal to 0. So we cross multiply by x to the 5th, and we have negative 7 plus 12 natural log x is 0. And then we'll have, natural log x equals 7 over 12. And then e to the 7/12 is x. Show that at this value of x, there's a point of inflection. So we need to go on either side. So we can check at 0. Nope, we can't. So we can check, we need to check on either side of e to the 7/12. So if you don't know, just put in the calculator, it says we can. So we can check at 1 and 2 into the second derivative. So the first one into this thing is going to be negative 7, and then natural log 1 is 0. So the 12 natural log x goes away. So we're going to have a negative over a positive. This is negative. 2, we're going to have negative 7 plus 12, and then natural log 2. That's a positive over a positive, so that's positive. So since it changes sign, so f double prime at e to the 7/12, or actually the second derivative, So the second derivative changes sign before and after the point of inflection. Okay, so now sketch the graph of f indicating the max and the point of inflection. Okay, so you see I've got the x-intercept. We should put on there x greater than or equal to 1, so actually none of this counts. We've got the maximum here, and that's e to the 1/3. And we have the point of inflection, which is like there. So that's at e to the 7/12. Okay, so, and then maybe we should put the horizontal asymptote.